During protein synthesis or translation, amino acids are covalently bonded to each other through peptide bonds. First, we're going to tell you how the peptide bonds are made. In order to do that, we need to go all the way back to the nucleus of a cell. Inside the nucleus, we find the DNA. This is drawn in red to show you just how protected the DNA is in the cell. This is never to come out of the cell. What needs to happen in order to get the mRNA strand is the DNA splits. The mRNA strand is built off of the DNA. Once that mRNA strand is built, it comes out of the nucleus into the cytoplasm where it meets up with a ribosome. As the mRNA moves through the ribosome, codons, or sets of 3 nucleotides, are translated. tRNA, carrying specific anticodons or complement matches to the mRNA, enter the ribosome, and the anticodon is attached to the codon. At the top of the tRNA, shown here as a yellow shape, are specific amino acids. When the tRNA leaves the ribosome, the amino acids are left behind and connected via peptide bonds. These will eventually go on to form proteins. In this picture, you can see many amino acids joined together by peptide bonds. The circled area indicates where the bond is formed between the 2 different amino acids. It takes many amino acids to come together by peptide bonds to join and make a protein.
We're going to talk about how the peptide bonds are made. Each amino acid is made out of amino group, hydrogen, carboxyl group, and R group, all joined together on off a carbon. The oxygen from the carboxyl group and 2 hydrogen from the amino group join together with the dehydration synthesis, making H2O. The carbon and nitrogen get bonds together through a peptide bond, creating a peptide group. Nitrogen loses the positive charge, and that is how the peptide bonds are made.
This picture shows the 4 structures of a protein: primary, secondary, tertiary, and quaternary. Here we see the primary structure of the protein, which we focused on, as this is where peptide bond formation occurs between the amino acids at the ribosome. Through the process of cooking an egg, peptide bonds are still not broken. As the egg is added to the heat, the proteins are being denatured. Weaker bonds, such as hydrogen bonds, are being broken. As the egg cooks, protein coagulates. This shows us that the new bonds, the weaker bonds that were broken before, are reformed, but the peptide bonds are still intact.
Even when scrambling egg with a fork, mechanically breaking down the weaker bonds such as hydrogen bonds and disulfide bonds, the peptide bonds are not broken. Again, we can see as the egg is poured into the heated pan, coagulation occurs. The weaker bonds that were broken now form new bonds. Through the entire process, the original peptide bonds in the primary structure of the protein remains intact. This is what happens when we eat the egg. When we eat, we mechanically break down protein by chewing. In the stomach, acid further denatures protein, but not able to break down the peptide bonds. Protein digesting enzymes like pepsin are secreted from pancreas into the small intestine. In the small intestines, then, the peptide bonds are broken by digestive enzyme into individual amino acids so our body can use it for energy.
The peptide bonds are covalent bonds, and due to the strength of the covalent forces, these bonds are not easily broken down during the normal heat of cooking.